Hello and welcome everyone. My name is Peter Robinson and this is Lewis Shriska, and he's going to talk to us about native rollups. So Lewis, over to you. Please introduce yourself.
Hello, hello. Hi, Peter. Nice to meet you again. Thank you very much for having me on. Yeah, I'm Luis. I'm the co-founder of Gelato. Been working on the project for 6 years, over 6 years. And I think especially last year, we made a lot of strides in the rollup space with our rollup as a service platform. We were behind powering some of the biggest chains that launched, like Kraken's Ink chain, for example, or Open Campus chain from Animoca, Lisk, and many more. And yeah, so I was already quite deep into the rollup research for about 2 years now. And recently, or like at the start of the year, got really pilled by Justin Drake's proposal for native rollups. Because I saw like with the first wave of rollups that we also supported, I saw still like a lot of shortcomings with the architecture. And I think native rollups are a really cool way to address certain issues with rollups around them being still, like very custom, like you have a lot of custom clients that have to be written. That usually requires then like security councils, upgrades, and so on. So most of the rollups today, they are really quite far from being like true to the original Ethereum spirit, I would say, of being like decentralized, permissionless, ungoverned networks. And yeah, so native rollups is one big research idea that is, I think, solving a lot of issues around how we can bring rollup execution back to the L1, and how we can standardize as an Ethereum network around rollup execution. There's also some other cool ideas put forth by Justin Drake, like based rollups, based sequencing, which also tackle other issues with rollups, but they're not they're out of the scope of the presentation today. So based sequencing is something else. Based pre-confirmations and so on. I think people familiar with the topic will also know about this, but native rollups is something different. Native rollup doesn't tackle sequencing per se. Native rollups tackle essentially what they achieve is EVM equivalence for rollups, and letting rollups use Ethereum's native execution engine to execute the state transition function on the rollup, which will lead. The hope is that this will lead to in the end game, the Ethereum layer 1 having like a way to verify ZK proofs for rollup that is built in. And then like you don't have to write your own custom ZK circuits anymore as a rollup, and maintain that and have a security council with upgrades and so on to be sure. Instead, you get like this sort of formally verified, very robust, always live ZK proving mechanic from the L1 for your rollup, and your rollup is essentially sort of natively like run by the L1 network. So yeah, that's like like turning your rollup a bit of from like, okay, this is like a sort of silo next to Ethereum to, okay, this rollup is now really like Ethereum native again. So yeah, that's what I will talk to you guys. What I will talk about today.
Wow, that sounds really interesting. So please present your slides, and yeah, shall we ask questions as you go through, or all at the end? What would you prefer?
Yeah, I'm happy to take questions throughout. I don't mind, whatever you guys prefer. So yeah.
All right, sounds great.
Can you see the slides?
Yes, we can.
Yeah, all right. So feel free to, ask questions anytime. So yeah, today I'm going to talk about native rollups, the future of Ethereum L2 architecture. I mean, this is debatable, right? Native rollups are still in research. There still needs to be a lot of lobbying and whatnot for this to happen. But essentially, there's already like a sort of like an EIP for a precompile, this execute opcode that I will talk about, which so like there's a standard path for getting this into Ethereum, but it will require a hard fork. So people project like early as 2026. Even the term L2 could be debated, I guess, in the native rollup context. But yeah, essentially, it's a new way to do rollups, which is more heavily using Ethereum's infrastructure than current contemporary versions of rollups. So yeah, what are the problems with current rollups? And again, like problem definition depends on what you're trying to achieve with your rollup. Like if your use case for your rollup doesn't require inheriting Ethereum security or properties and so on, then probably native rollups are not for you, like not interesting for you. There's a ton of use cases we know from our customers that we have in Gelato, where you actually don't need like World War III, whatever, robustness, whatever the Ethereum pitches, right? Like, so there's still a ton of use cases outside of native rollups for rollups and L2s. That's totally fine. But if you identify with Ethereum and you think that you want to build like on Ethereum, you want to build your rollup application as close to Ethereum standards and properties as possible, then I think native rollups are really like an evolution that is gonna have some unlocks for you versus what we have today. So yeah, current rollups face significant challenges. You have complex custom verification. So you have thousands of lines of. By the way, I'm just quickly gonna move this here so I can also see your face. Is this fine for the screen recording, or is this annoying if I put the faces here?
Oh, that's okay. We're not even seeing it.
All right, good. Okay, cool. So current rollups face significant challenges. We have complex custom verification, thousands of lines of fraud-proof games or snark verifiers with high vulnerability risk. So, if you're familiar with OP's code base or Arbitrums or any of the ZK EVMs, like there's essentially a ton of code that just deals with these fraud-proof games, those ZK circuits, and some of like I think OP is one of the champions of EVM equivalents, staying as close to standard EVM as possible. And of course, nowadays you have things like SP1 from Sasync, which is like allows you to prove ref. But like still in these early versions of rollups, usually we see quite the departure from standard EVM, especially like something like Arbitrum. They, I think, have gone quite far away from standard EVM implementations, also with their WASM builds for Stateless and so on. So yeah. And the problem is that essentially, if you want to build a rollup today, you need to have this custom rollup state transition functional verification mechanism, like commonly known as prod proofs or ZK proofs. So this introduces a lot of risks and maintenance costs. Let alone the fact that some of these proving circuits might have vulnerabilities. If you have like if you are on your own island with whatever proving circuit you use for your rollup, and you have one like incorrect bug in there or something, like it could be very fatal. So this to manage this risk, what rollups nowadays usually do, L2s, is they introduce a lot of centralization. So you have security councils or centralized sequencers as safeguards. So it's sort of like centralization as a feature in a way, because it's like there to protect you against bugs and so on. There's contract upgradability and so on. But at the same time, it's like a departure from Ethereum L1, where the whole point is like, okay, it's immutable sort of immutable code, or rather it's an immutable blockchain, really, right? Like, so your rollups usually are not really immutable blockchains. They have all sorts of upgrade mechanisms and councils to govern that. So yeah. And another issue with rollups now currently is that you have manual EVM upgrades. So if Ethereum hard forks, like recently I think it was Pectra, introducing new opcodes like for 7702 or whatever it is, your rollup has to do the same. And given that a lot of rollups nowadays have a lot of custom code, it actually takes time for them to become equivalent with the L1 again, right? Like, so OP usually again is the most equivalent. They usually are the fastest to upgrade, but something like Arbitrum, which is already a bit customized, they for example took longer, and not that much longer. They're a big team of great engineers, right? But they also took a bit longer to enable 7.702, and I think there's still many rollup ecosystems out there which haven't upgraded to Pectra yet, and which will still need more time. So this is also an issue. And then you have expensive on-chain verification. Today, your rollup settles on Ethereum, and the proofs, whether fraud proofs or ZK proofs, currently have to be run on chain, like the verification for your rollup to have verified settlement on Ethereum. So essentially, rollups today in this early version of rollups are separate systems with their own trust assumptions. The original intent was for them to be just like Ethereum, inheriting Ethereum security, but in practice today, they're actually quite far from this. They introduce a lot of trust assumptions. So what are native rollups? Native rollups use Ethereum's native execution engine directly. This is done via the execute precompile, which exposes Ethereum's built-in EVM execution engine to rollups. And the difference here is just like, instead of essentially rollups can just call this precompile with transaction traces, and instead of building their own custom verification. So if you think about how would a current rollup upgrade to become a native rollup, like how would a current rollup migrate to become a native rollup? Essentially, they would have to isolate the sort of proving of their state transition function and or verification of the state transition function just completely ditch it, and instead just call this L1 precompile, and then Ethereum, the network, sort of handles the state transition verification and proof verification. So this is really cool because like if this works, like the idea is you can just build a rollup and you can just call this L1 execute precompile, and then your rollup state transition is advanced, and the whole Ethereum network is sort of verifying that and doing that for you. And Ethereum validators in the naive way, they just re-execute or verify, in the naive way, they just re-execute the trace, or in the more scalable way, there will be ZK snark proofs, and they just verify the proofs off chain using diverse ZK execution clients. So you can think of this as today they run Geth or Reth. In the future with native rollups, they will run like a ZK Geth version and a ZK Reth version. This will allow them to if your rollup is proven with SP1, for example, there might be like an SP1 Reth version on the layer 1 that validators run, and it will allow them to verify your rollup with a ZK proof from SP1, for example, or any of the others, ZK VMs like RISC-0 and so on. So it requires validators to run new software, these ZKEL clients. There's a lot of questions about assumptions like around, hey, what about minority clients and this and that. There's a lot of detail there, but ultimately you can just think of, hey, the L1 can now verify your rollup, and you don't have to build your own verification circuits anymore and have them audited and so on, and your own prover and so on. Like all of this exists as infrastructure on the L1. All you have to do is call this execute precompile with the correct format of we will look at that in the next slide. So the key benefits are you eliminate custom verification systems. You have trustless rollups that really inherit the L1 security. And there's some cost benefits also from batching efficiencies. So Justin Drake sometimes says that these are like programmable execution shards that wrap the precompile. Like if you go back to Ethereum lore a couple of years ago, that we were talking about shards. execution shards, and in the case of native rollups, they're not direct copies of the L1, so they're not just like execution shards, they're more like programmable execution shards, because of course you still have your own state on the rollup and so on, but the cool thing is the L1 doesn't have to keep all of your rollup state, because you have the stateless verification essentially with these, just by providing for every rollup state transition that you do, you provide the full state access and traces. People can re-execute it, or with ZK verify the state transition function cheaply, and they can discard the state, like they don't have to keep it on the L1. So there's no added overhead for state, which is really, really good. So yeah, this is the execute precomp. Yeah.
On that last slide, so there's this execute precompile. So I submit a transaction to L1, and in it, it's got a execution trace, and I pass it in as data to the precompile. Is that how it works?
So here's a slide where we go a bit more into the precompile.
Right,
So the precompile has the pre-state root and the post-state root, the trace, and gas used because we still have to make sure that we don't overload the L1 validators, and we shouldn't be able to DDoS them, right? So there's still a notion of gas here. But essentially, you just need to have the correct format of like the trace, and then like the assumption is that the L1 validators essentially they get proofs off chain for your rollup. They know, okay, your rollup is this trace is like, it means that you're using, let's say, SP1 or yeah, you might have to provide multiple traces if you want to have multiple provers to be able to verify, or multiple proofs for your rollup. You know, validators shouldn't just run one proving system. That's very key to understand in this early spec of the execute precompile. The idea is not to enshrine one specific ZK VM, because that would also reintroduce some of the issues around, okay, what if there's a fatal error in that ZK VM and so on. The idea is still to keep the tenet of multi client diversity. But yeah, ultimately, your rollup your rollup can now be proven on the L1. You just submit the batch, which is like the traces, the trace of transactions and everything that was done in that rollups block that needs to be available to the L1. I'm not entirely sure how it's stored. Don't think, like, I'm not sure how blobs come into play and so on. But ultimately, the trace of the transactions that moved your rollup state from pre-state root to post-state root needs to be available, and then the L1 validators, they can either re-execute it to verify your rollup state transition function. That's the early naive implementation. Or really what we're going towards more is like that they will have, like off-chain, they will have proofs for your rollup, and then they can just verify the proof, and then you can really have like a lot of transactions in there in this trace. And your rollup can really scale. Interestingly, there's also an optimistic version where you just submit all of the you call the execute precompile, and no one verifies it unless they're challenged, right? This is also an interesting model. So and then in the challenge you need to provide the transactions trace and so on. You need to make sure that's available. So yeah, versus in the ZK one, the goal is that everybody can also generate a ZK proof. So the trace always needs to be available in the ZK version. So for ZK native rollups, they have to be real rollups. So they have to make all of their data available on the L1. Versus for same for the naive re-execution one, like we could call them pessimistic rollups, where every validator re-executes everything. For optimistics, you could also have like optimiums, right? Like, so you could have a native rollup that uses Celestia or something for DA, and only when someone challenges the rollup state transition function on the L1 do you need to come and provide the trace of transactions, everything, make that available. and then you run a fraud-proof game on the L1 with the L1 validators. But yeah, I haven't focused too much on the optimistic case. I usually only like care about the ZK case. But yeah, so that's the idea. Like the rollup sequencer is still there, and the rollup sequencer just posts the batch of transactions in the trace, and it calls this execute precompile, and you know, the validators will the native rollup has to be EVM equivalent, right? And if it's EVM equivalent, then the validators will be able to use some of the common provers like SP1 or something to get a proof and to verify this rollup. And I think there's like even a role where in the future you have like execution proposers, and I think the idea is that they have to include like proofs in the block for this native rollup, and they think to be able to propose the block and so on, they have to post a bond, and they need to include these proofs. So yeah, and of course they need to be compensated, like, because where do these proofs come from? They come from proving services, prover networks, and so on. These prover networks have to be paid. Yeah, so yeah, then there needs to be a payment as well for this. But yeah. So the validation process is process trace from pre-state root, confirm execution produces exact post-state root, verify precise gas consumption. Yeah, the resource management is still, like, I think, an interesting topic. But yeah, you like the L1 block proposer sort of or builder, like they meter the cumulative gas across all execute calls. Yeah, so yeah, you have multiple, you can execute multiple rollup state transition functions inside a single block. But there's this execute cumulative gas limit to prevent DOS attacks as well. Yep. Stateless verification is very important here. The idea is that we don't want to have state bloat resulting from this, right? Like, so validators shouldn't have to store any rollup state. Validators confirm state transition without storing full blockchain state, so rollup state. They use these state access proofs to reconstruct needed state data, and then this shifts validation from a storage intensive to a computation focused task for these L1 validators. So as they really, what they have to do is just verify your rollups. And in the world of ZK, this is like computation wise, this is really efficient as well. Yep. And for native rollups, validators only temporarily have to hold the complete execution trace. And in the phase one, the proposal is to have re-execution. So like I mentioned earlier already, validators just get the trace and they literally re-execute your EVM, your native rollup EVM directly, which is not scalable at all. But the cool thing is it's already like using Ethereum validators to run your rollup state transition function. So I don't think there's any scalability unlocks here. So it's not meant to be like a long-term scaling solution. But it's already a cool proof of concept, because it shows that Ethereum can be used to run your rollups natively and the execution of your rollup state transition function at least. And then the upgrade path from there is to ZK Snugs, where they use the trace to verify the format, but then they just rely on ZK proof verification for verifying the correctness of your rollup state transition. Yeah, I think there's some trade-offs here, like this ZK or in general native rollups introduce a bunch of DA overhead versus current rollups. But yeah, that's like a trade-off. They're a bit more costly on the DA side, but I think the scaling roadmaps for blobs is pretty massive anyway, so I think DA shouldn't necessarily be a huge cost factor in the future. Yeah, the different verification approaches are re-execution at launch. I don't want to explain it again. And snark verification. What's important to mention about the ZK architecture is that there's no standardized, like no king-made ZK VM. Each validator uses their preferred ZK systems. So they might use, succinct SP1, RISC-0, whatever. This means that you need multiple proofs to be generated. So like one native rollup with a trace may need different formats for different ZKEL clients. The only standardization happens is at the consensus layer, where the state access format is standardized, but not the ZK implementation itself. So what this means is like, nowadays we already have client diversity, and institutional validators normally would run multiple clients. There's even this project called Vouch, I think, where you can run like multiple clients in parallel, and it sort of resolves to like to a system where it detects like essentially faults in clients. Here, the problem is that this is very expensive today on Ethereum's execution layer to run multiple clients because of states essentially. The idea is that with native rollups, this will be much more efficient, because these ZKEL clients can be pretty stateless, and you can easily run multiple of them for not much added extra cost. But it's certainly still a question. Okay, what about minority clients, ZKEL minority clients, and so on? But ultimately speaking, we can think of L1 validators running, probably, at least that's the design goal, like running a couple of these ZKEL clients, and the idea is for there to be a good distribution among like the top 3, 4, or 5 clients. And then you literally have multiple proofs for the same transition function that get verified, so that every validator, no matter what client they run, can verify the state transition function of the native rollups. But here, to be honest, I'm also still a bit fuzzy on it. I definitely have a lot of questions myself about this aspect. Because we at Gelato, we actually were one of the only RASes who ever ran a full-on ZK EVM in production back in the day with Polygon. Over 1 year ago, we run a Polygon CDK chain called Astar in production, and we saw how crazy expensive the proving costs were back then. So the idea of having to run multiple different provers for the same state transition proof just for redundancy is a bit crazy, because proving was so expensive. But I think the idea here is that proving is gonna be so much cheaper now with the recent advancements in the technology, that actually it becomes feasible to create multiple proofs. But yeah, again, I'm a bit fuzzy on this. I think there's still some open questions around this multi-proof system. So let's look at the native rollup verification approaches. So essentially, we have the native rollup. It pulls this state transition data, right? Like the trace, this pre-state root, post-state root to the execute precompile. The execute precompile is run natively on the L1. And so here on the left side, we see the simple re-execution approach. This is not using ZK snarks, very simple. Every validator, just like on the normal L1 execution, they pass the execution trace, they load the state tree data, they execute every transaction of the rollup, and then they verify the state transition. So again, this is very naive. It's not scaling really at all. But it is verifying the rollup on the L1, which is like the proof of concept. And then approach 2, again, we're not mentioning the optimistic approach, which is also there. It's also cool, but we're focusing on ZK here. And for the ZK approach, it's more like you have different provers, like RISC-0, SP1, or Jolt, which all generate proofs of state transition correctness. And then your validator could run all of these ZKEL clients, or maybe you just run the RISC-0 client, and your friend's validator runs the SP1 ZKEL client. But the idea is every validator on the network gets a proof that matches the GKEL client to simply verify the rollups state transition functions with a ZK snark proof. And again, like you could simplify the system a lot by the Ethereum L1 mandating a specific ZK VM. This would be much simpler to reason about. It's like, okay, every validator uses the same ZK system, the same ZK EL client. But here, I think Justin Drake is pushing very hard for like a more open market, so that we don't enshrine one specific ZK system, which might have a bug in it or might become overhauled by better solutions on the market quickly. So the idea is for the system to be more agnostic and to let the market find the best systems and make the whole native rollup L1 system be agnostic to whatever solution is on the market. Yeah, but still, like I still have some questions about it. Yeah, but I think the simple idea is like, as long as your rollup can be proven by one of the majority clients, you should probably be fine. And you can just call this execute precompile, and someone will prove it for you, and you know, the L1 will be able to verify the rollup, and your rollup can be run on the L1. All right. Optimistic versus ZK native rollups. So optimistic native rollups can use AltDA because they only have to make the rollup data available when challenged during disputes. So this means that their batches can also be quite large because we only need to verify the disputed segments in this fraud-proof game. However, the finality is still pretty bad, as we know from optimistic rollups, right? Like, because you need a long challenge window. So it's you know, anything on the order of 7 days or maybe 1 day for ZK fraud proofs, but still very long. Latency is introduced by the optimistic approach versus the ZK approach. There, all of the data has to be on Ethereum. Like, validators need immediate access, so the data needs to be included on the L1 for the native rollup. And there's so there's also a constraint of this execute cumulative gas limit. But this constraint, I think, can be huge. Like, we're talking gigagas or teragas at some point, even once we have the ZK future, because of the nice you know, scaling benefits of ZK for verification. And the where ZK native rollups really shine is finality, because they enable like real-time settlement with 1 slot delayed execution. So like, you know, like your proof, your ZK proof sort of comes almost like at the same time as your rollup data. So you can settle the rollup immediately on Ethereum, not like with optimistic rollups where you have to wait for a challenge period to elapse, which I believe has huge economic benefits, because actually there's a lot of hidden costs to having slow finality for rollups. We see this nowadays with these 7-day windows on optimistic rollups, like market makers moving funds in and out of the rollup, like via a cross or any of these systems, requires a lot of capital intensive operations, versus when you have ZK rollups, like, and your rollup settles within like a block or two. You know, like, it's very much faster to move funds in and out of the rollup via the rollup bridge. So yeah. And there's this other aspect of this 1 slot delayed execution that you will hear a lot about in the context of native rollups, and especially ZK, where the idea is, like, in the future, Ethereum will introduce another sort of upgrade to the system with 1 slot delayed execution. And the nice benefit of this is that it also has this unlock where you have more time to generate a proof for your rollup. And I'm not super well versed on this aspect, but I think the idea is that it sort of there's less centralization risk from super beefy prover-proposer setups where someone can generate a proof much faster than you all the time, and they win all of the block proposing rights and so on. So yeah, that's my understanding of it. I think we will revisit that briefly later. Current Ethereum consensus limitations. Yeah, so let's quickly talk about some of these adjacent proposals, like Attester-proposer separation and one slot delayed execution. I won't go too deep into it because it's not really the scope of this presentation, but it's something that you should also research as you research native rollups. You will see this Attester-proposer separation idea and delayed execution coming up, popping up a lot. So currently, proposers handle consensus and execution, and they receive all of the rewards, and attesters vote on block validity for finalization. The problem is that a single proposer must do both jobs in 12 seconds, so they must, I mean, there's proposer builder separation, but ultimately they, in their slot, they must achieve consensus on the block ordering, and they must execute the block. So this is not a lot of time for intensive cryptographic operations like generating a ZK proof. When we say real time is maybe a bad word. What we mean is like real time is within one slot, and right now within one slot means that you need to be able to prove a full Ethereum or native rollup block within 12 seconds, which is not a lot of time, given where we are at with ZK proving software and hardware today. Yeah, so what we need is we need to have a separate timing for consensus versus execution. And here this idea of Attester-proposer separation, which is on the Ethereum roadmap, comes in as well, where we have a role separation. So we have these beacon proposers. You can think of them as the most lightweight way to run like an Ethereum validator, where you only do consensus. This is similar like to when you run a validator today, and you use MEV boost and like someone else is the builder. So yeah, these beacon proposers, they only take care of consensus versus like this new role of execution proposers. You can think of these execution proposers a bit more like builders in the current sense, although PBS is compatible with this as well. But execution proposers handle the actual block execution, and then you still have builders like that you can, like execution proposers, I think, could work with builders with PBS. And then there's this new timing structure, which is like at slot n, we simply just propose the block. And at slot n+1, the execution proposer, I think, basically proposes the state root for the previous block. And the cool thing is that this gives execution proposers a full 12 seconds for snark generation instead of just milliseconds. And this levels the playing field essentially. And overall, the idea is that because ZK proofs are so important for native rollups to work, and the L1 needs to make sure that ZK proofs are generated for this execute precompile. Yeah, the idea is that instead of having there being like this centralization race where, like the only way to participate is if you are essentially producing the proof really, really fast. You now get like a full 12-second slot to produce the proof. Again, I'm not the best guy to articulate this. I still have to research this a bit more. But I think this is the overall idea is with Attester-proposer separation is to allow for more participants in this new execution proposer role, and more participants that can generate proofs for rollup blocks. Yep. So delayed execution and proof generation. So delayed execution is also another concept where validators approve blocks before executing transactions. And there's this idea of again, you can think of it like, okay, you propose a block, and then in the next slot you and then in the same slot you execute the block, and then in the next slot you sort of have the state root of that block, and you propose that, and then attesters can attest to it. And essentially, this should make Ethereum faster because you can achieve consensus without executing everything. You can just achieve consensus on the contents of the block quickly, and then you execute in the next block. So there's like this lockstep mechanism. And one-slot delayed proofs is also an interesting concept where it's essentially here in this diagram, you can see the idea is that on slot N, we get these execute calls and state transitions, everything. We then have time to generate the proof in the ZKEL client, and then in the next block, we verify this previous block with a proof, and this doesn't all have to happen inside one slot. So this is the unlock here. Essentially, it's just allowing for the real-time proving constraint to not be within one slot, but to have this sort of lockstep mechanism where you have more time to generate proofs, which means like more validators can participate in this proof generation process. And then you sort of verify the previous block now that the proof is ready in slot n+1, and then the same time at n+1 you execute the next block, and you achieve consensus on the previous slot, and then it goes on. It's like this sort of lockstep mechanism. But there's also like a proposal for a same slot proof solution. I won't go into this, but like there's a new proposal where builders prove their own blocks to claim rewards, and if they're missing proofs, then there's like a automatic no-up execution. Yeah, so but I won't go into this. There's like a lot of research happening here, but like I would summarize all of this in okay, how much time does the system have, this market have to generate proofs for native rollups, and who are the participants that can participate? And usually the idea of these like design goals are, hey, let's make sure that the system is always live, like the system always generates the proof, because remember, the whole idea is with your native rollup, you don't need to take care anymore about like your own proving circuits and so on. This is like a service that the L1 provides to you. So that service needs to, like Ethereum services mean they are always available, right? That's the point of Ethereum. So I think all of these ideas are just like, how can we design the system and the constraints in such a way that the L1 service providers essentially have enough time to generate proofs for there to not be too much centralization vectors, and for there to be for there to always be proof generation like happening on the L1, and the incentives around it. So like this is like how I would broadly summarize this whole idea. So yeah, the technical benefits are security and trust related. You basically can say that now your rollup inherits the security of the L1, because the L1, validators, they will like socially coalesce around a number of ZKEL clients, similar to how today we have Reth, Geth, Nethermind, and so on. And these clients will be, there's client diversity, which is great, because then if one of the clients has a bug, it's not so like the network can still operate and your rollup can still function, unless all of the clients have the same bug, which is less likely with diversity. And at the same time, you benefit from everyone, the whole native rollup community, sort of compounding around like a set of clients that will be formally verified and so on. And it sort of eliminates this need to write your own custom fraud-proof games or ZK circuits, and you can just use what like the community has already developed, and you get some lindiness from that, I think, over time. Let alone the huge costs and everything, the capital you would have to raise to build your own ZK circuits, or yeah, the idea is that Ethereum gives this to you as a service and you don't have to go away from Ethereum anymore. You get EVM equivalence because you run this natively inside the EVM L1 execution engine. So when the L1 updates, their EVM, your rollup automatically gets this update as well. So in the future, if you're a native rollup and there was going to be another Pectra-like upgrade introducing account abstraction like 7702 and so on, your rollup immediately gets that upgrade as well the moment the L1 has it, which is really cool. Cross rollup composability. This design lends itself more to trustless state verification between rollups and direct ZK interoperability. There's also ideas of combining this with base sequencing. And operational simplification, like rollups become Ethereum extensions. They're not really separate systems that have to be governed separately by security councils and so on. And you have a more unified security model that reduces the ecosystem fragmentation that we see today in the L2 landscape, where you have like, I don't know, LP superchain governance and this governance here and there. And see, like, we have a lot of single rollups at Gelato that are essentially just governed by the rollup rollup operators, and instead you sort of have this, okay, this is like more like Ethereum again, where the L1 essentially runs your state transition function. And I think this is also the way to have immutability at some point again. Challenges: there's more DA overhead from this. That's one of the drawbacks. Initially, there's still a lot of constraints around how much gas can be consumed with this new execute precompile. Although the idea with ZK is that this will really be massive. You have a lot of migration complexity. If you're an existing rollup and you want to upgrade to become native, there, you probably need to really have a huge refactoring. And there's a lot of standardization that needs to happen around interfaces for the rollup bridge. And then on the roadmap, there's a bunch of ERPs and hard forks needed. Like, you need the execute precompile. I think one slot delayed execution is also really something that native rollups want for their ZK versions. Again, I didn't give the best explanation here today, but I think that this is essentially all around coordinating a ZK proving market that doesn't just collapse to like a single beefy ZK prover. And the timeline here is likely not before 2026, might even be longer. And there might be a phased rollout where we start with simple re-execution on the L1, so no ZK, no optimistic native rollups, nice proof of concept. And then at the end, we might have like a full snark verification at some point. So yeah, conclusions. Today, fragmented rollups with separate trust models and complex bridging. And the native rollup vision is to have unified security. All rollups share Ethereum's properties and guarantees. Seamless interoperability, cross rollup transactions without trust assumptions are become possible between native rollups, and potentially at some point even between a native rollup and the L1 itself. And overall, like, we would get much more capital efficiency, because more rollups will be able to move to ZK, because ZK essentially is something that ZK rollups is something that exists on the L1 as a service for rollups. And yeah, the development of rollups is sped up and simplified, because if we're willing to be EVM equivalent, we have these sort of services that the L1 provides for EVM equivalent rollups. You don't need to write your custom EVM verification anymore. And you have these automatic upgrades as well with the L1. So yeah. Supporting infrastructure, like I mentioned, shared base sequencing can be combined with native rollups to great effects. That's the hope. A lot of ZK VM infrastructure is needed for like this sort of real-time proving. Even with this one slot delayed execution mechanism, you still need a lot of very good ZK VM infrastructure. So like the Sasing, Gris0 teams, all these teams are building that. Yeah, so the end game for Ethereum's L2 scaling is sort of blurring the lines between the L1 and the L2. Yeah, I also have a full podcast where I discuss this with the man himself, Justin Drake. I think this QR code should link to that. And we also have a write-up on the Gelato blog, gelato.cloud/blog, I think, about native rollups. So definitely make sure to scan these QR codes as well, and read the blog and watch my, like, I think 2.5 hour long interview I did with Justin Drake. Although, spoiler alert, actually I wanted to cover native rollups with him. We only briefly touched it. We talk a lot about other things like base sequencing, pre-confirmations, beam chain, and so on. He promised me that he'll do a follow-up with me, sort of a part 2 where we just talk about native rollups. And that's it. Peter, I have some, I think, that's your stuff, right?
Yeah, it is. So the merch store is still open. Please grab a t-shirt. Maybe I should have a native sequencing or native rollups t-shirt, but anyway, to come. Next slide, please. Yep, there are a whole stack of talks coming up. Next week, actually, we've got one on Maiden, and then some weeks after that, we've got a talk by a team that are doing a different way of Ethereum data access, so not subgraph, something else. I've decided that we really do need a talk on 7702, so I'm going to talk about that. And then we've got Paul Bowes coming along to talk about Circle Currency Protocol. Next slide, please. And there are a whole heap of social links. Yeah. So if you're here today, it's on YouTube. If you're watching on YouTube, please come join the meetup. Then you can ask tricky questions live. Yeah. And
Cool.
are there any questions? So I put some in the chat. Given the big storm here that was happening here, I wasn't sure if anyone would hear me anyway. So I think one of them was a point that my understanding is that trying to execute multiple ZK in parallel is too expensive, but let's move along from that. So we've got this execute precompile. So you submit a transaction to Ethereum and it's got some trace in it that ends up in the blobs. And then
I think you still, like with native rollups, you still have a sequencer, a rollup sequencer. So you can still have a centralized single sequencer and you can submit your transactions to that sequencer. I think the idea is more like that sequencer doesn't essentially the rollup state transition function or the state proof is not also generated by, like, normally with rollups today you have like a prover or validator system or something like that. And here instead, like as a sequencer, you don't have that anymore. You don't really care anymore about your rollups for proofs or whatnot. You just use the execute precompile, and you give that precompile like, okay, look, this is my previous block. This is like my pre-state route. This is my post-state route, right? And here are all of the transactions. And you might have, as the sequencer, you might have already run all of this, right, on your ref client or whatever it is, on the rollup. And the L1 now essentially verifies that what you've done was done correctly. And here the magic is that the L1 essentially, like I would say, the magic is that there's been standardization around the ZK-EL clients and your rollup being EVM equivalent. And if your rollup is EVM equivalent, what you will give to the L1, the format of the traces and everything can be parsed correctly by the L1 and proven and verified. And then the L1 sort of moves your rollup from state A to state A+1, right? But the users still, like, they might not interact with the L1 in the sense that they give the L1 their transactions or something. That might still all go through a centralized sequencer. It's just that this sequencer isn't tasked with also posting proofs to the rollup L1 contract anymore. That is sort of natively done and run on the L1.
Okay. All right. So I guess it's part of the process is taken on by the L1, but it's still like the transaction to transaction trace is being done by, say, that sequencer. And then the L1's just taking on faith that that trace is correct. And because it's just saying, that state plus that trace equals this other state. It's not saying anything else.
Yeah, but that's enough. Yeah,
Mm.
that's enough.
Yeah.
So you still publish the data on the L1, right? So in the ZK sense, you always publish it. So yeah, you have the data inputs, you have the pre and the post state root, and you have a proof off chain on the L1, and all the L1 validators can verify this, and they can then run the execute precompile, and it's like an assertion. And the idea is, okay, if the execute precompile is correct, like if you can verify that with the proof you get that this is correct, then you will update on the L1 like the state of the rollup, right? And this like the way I think about it is against this new state root, once like this is in the rollup bridge, right? Like, and then users can withdraw from this rollup if they want to exit it against this new state root. So they are secured by the L1. Because the L1 only updates the state of the rollup against which you can process your withdrawal, right? If it's the computation is correct, and it verifies that for you. So yeah, that's the idea. But the ordering of the transactions, that's completely still mandated by the sequencer. Right. So and this is also a feature, like many rollups actually might not want to give sequencing rights to the L1, right? They might want to have a centralized sequencer for maybe they want to protect their users against MEV or something, I don't know. Or maybe they want to extract MEV. Yeah, so that ordering is still done on the rollup. Like that would be base sequencing and pre-confirmations. That's another topic where the L1 becomes the sequencer of the rollup.
Yeah.
I just have some questions. Hey. Hey, I just have just a question around the block plus one, where you submit the proof of block later. Is that going to be for L1, or is this only for the execute precompile kind of thing?
Yeah, so caveat, like APS and delayed execution, I touched upon it. I haven't revisited the topic in a while, and I would need a refresher on it. So like a lot of this is still in research and so on, right? So I can't give you like any guaranteed truths here, right? Like I would encourage you to read up on these topics. They are related to native rollups in the sense that we hope to get some unlocks for native rollups from these topics. But I think delayed execution is something that is not just for native rollups. That's something just like APS, Attester-proposer separation, is like things that will be on the L1. It's just that they will bring some unlocks for native rollups. And I think the unlock for native rollups is really for ZK, is this idea that you can let the L1 validators generate proofs for these native rollups within a time band, and instead of just like there's essentially like a delay where that gives them enough time to generate a proof, which is leveling the playing field sort of, versus if they have to like bring it in, I think immediately, then there's like a sort of latency game. This is the way I understand it. Like if you don't have this mandated delay, then there's like a latency game which can lead to centralization, where it's like, okay, whoever is running the beefiest ZK prover setup can propose all of the blocks because they can run all of the execute functions. Yeah.
And so I was thinking though, is if they don't generate a proof in that next block, is the block essentially uncled and just like you skip over it and is a reorg essentially?
Yeah, it's a good question. I haven't touched upon this in this presentation. I don't know where the research is here right now, but there was this issue of, okay, what, like essentially you're asking what if there's no proof, right, on the L1? Essentially, this would be like, in a way, you could like, this would be a bit of a catastrophic failure, because the whole point of native rollups is this is comes as a service from the L1. And what is Ethereum there for? It's for 100% availability of the service, right? Like the only reason people use Ethereum is because it's always available, right? Unstoppable, right? So like I think if you had a scenario where even though you do everything right with your native rollup, right, you still don't get the proof, and your execute invocation is not like run properly or honored, this I would say is like a failure mode of the system. I'm not sure where the literature is here today. Like I mentioned this briefly on the slide, there was like some don't think I linked it on the slide, but there was some proposal like a month or two ago already for how to handle this. I think the idea would be around, okay, in this new system with execution proposers, they actually have to be bonded. So they might need a 1 ETH bond, and they have to bring proofs as well. And the idea is that their bond is higher than the cost that they have for generating proofs. And then they're incentivized to bring these proofs. Yeah, that's the idea.
Okay.
Yeah, but ultimately it's about incentives, right? Like in this block production pipeline, people should get paid enough to include your execute invocations, and for them to work, you need proofs to be available, right? Because otherwise, if the attesters can't verify the block and so on, then yeah, there's like yeah, no way to include the block, I suppose.
Okay, cool, thanks.
Yep. But again, research is still out. I think Ethereum also doesn't really have like a Bible like big doc for this topic yet, so I think they're working on it, but this is still very early research stuff. I think the original proposal from Justin Drake was like in January of this year or something like this, the original post.
Yeah, I got the feeling talking to a few people in EF and others who are looking into this sort of thing that it's still a way off. And it just feels like there's a lot of options. And when there are a lot of options, then it'll take a while to narrow it down. And I think I can see you've got a level playing field having the extra slot. It means that there's a 12-second latency suddenly on all the transactions, unless you could have some sort of pre-confirmation step where you get, instant confirmation that we've included your transaction. But I guess you're not saying whether it's going to revert or not, though. So, yeah.
Yeah. Yep. I think there's abstraction layers there where ultimately the idea is just for the L1 validators to benefit from this delay. But at the user layer, I'm sure there's like going to be pre-confirmations and so on so that for the user, like they don't notice this this delay. Yeah, and probably once like in step one, once you already have consensus, then I think it's you can get a very good pre-confirmation from this because you can be sure about the ordering. And when once you have the ordering, you can execute. Yeah. So yeah, it's really just about L1 validators, I think, that are running on, like Justin Drake always talks about smartwatches nowadays and so on. Like for these guys to not have to be able to verify ZK proofs and rather for proof generation to also still remain somewhat open and decentralized, like for enough people to have time to generate their own proofs if they want to.
Okay, look, I don't have any further questions. Does anyone else have any questions, Tim?
No, I'm good.
Okay.
Thank you.
All right. Well, look,
That was great.
yeah, it was great.
Thanks.
Thank you very much for your talk today, despite challenging circumstances, at least for me. But yeah,
It worked out fine.
Yeah. Well, it's still raining, but it eased off, so it's not too bad. So thank you very much. Yeah, this has been awesome. I'll put the video up in sometime probably tomorrow, and you'll put the link to the slides as well, and so everyone will have access to them.
Cool. Nice.
All right.
Yeah, thanks guys. It was a pleasure and see you later.
All right. Thank you. Bye-bye.
Bye-bye.